Propulsion DBT is a design, build, and test research course, giving students the ability to actually conduct research and make and test a gas turbine engine. In this course, you'll work within your team with a real budget and with industry mentors to actually build and test a palm-sized micro gas turbine. A gas turbine is used in all different types of aircrafts, from jets to drones to military aircraft, and works off the theory of combusting a fuel with compressed air, using that combustion product to drive the cycle over again, and create thrust or spin a generator for power generation. Specifically this semester, the team has begun developing a small-scale micro gas turbine for power generation, with its application in drones to replace the low energy density found in batteries that most drones use. What's more is we're designing it to use hydrogen as its fuel, which has a lot of interest in the industry right now, and it produces a very clean and green product in its exhaust, which we all use: water.
Scaling down a jet engine is an incredibly challenging task. Conservation of the thermodynamic cycle means we want the same energy exchange between components at a much smaller mass flow rate. This results in very high RPM, makes maintaining structural integrity very challenging. On top of this, we were limited on budget and time, so machining and material capabilities needed to be considered during design.
We selected a centrifugal compressor design to produce the required pressure ratio, which is almost 3.5 times that of the atmosphere. With a centrifugal design, this can be done within a single stage as compared to multiple stages that would be required in an axial compressor design. To match this compressor, we designed a radial turbine that expands the combustion products and powers the compressor.
We tested dozens of design parameters for the turbomachinery, starting with a parametric analysis, which ended in 3D design theory and CFD. ANSYS Workbench helped connect our first principle design with full 3D rotating CFD.
The complex geometry of the rotors was fabricated using a 3D additive manufacturing technique known as DMLS. The compressor was constructed out of aluminum, and the turbine was constructed out of stainless steel to withstand the high temperatures. Next semester, we hope to have a higher budget to manufacture the turbine out of high temperature resistant nickel-based superalloys.
Material, geometry, and features were all things that changed through our design process. Our overall profile nearly doubled after the PDR. We realized that under optimum conditions, our compressor required nearly 20 kilowatts more than the turbine could actually produce. After running our design through
The design iterations after CFD analysis were sent to the structures team to perform FEA on the rotors. After input from the structures team, changes were made to the blade thickness as well as the overall blade profile to maintain structural integrity of the rotors.
Aside from structural loads, we also had to focus on the thermal load analysis as well. Because our combustion chamber is so size constrained and the temperature of hydrogen combustion far exceeds the temperature of our working material stainless steel, we iterated through many different designs. CAD was passed to CFD, which was passed back to CAD, and the cycle was continuously performed in order to produce our final design.
The turbomachinery will experience extreme conditions at full throttle. At the design point, it will spin at nearly 100,000 revolutions per minute, and the turbine will experience a temperature of almost 1700 degrees Fahrenheit. Therefore, special considerations must be made to the design and manufacturing process of the turbomachinery.
An important part of the design process is to ensure that the parts do not fail under use. Although our entire architecture involved minuscule parts, they had to withstand a high structure and thermal loads. We started by selecting relevant materials and went on with the thermal analysis. Our results indicated that the heat dissipation was high, so we had to run structural analysis based on those elevated margins. One of our crucial concerns was the stress concentrations, which we solved through an iterative simulation. We also performed a vibration analysis and found that the resonance occurs at lower 80,000 RPM for our system.
One of the best parts of the class, in my opinion, was the feedback we got from people within the industry at every step of the design process.
We leveraged the years of experience of engineers from Rolls-Royce and Kratos to inform our design choices, manufacturing plan, and test procedures.
They were able to give us feedback on how commercial companies approach the same issues we were struggling with and give tips on the best ways to approach those design problems. We got a lot of help designing the shaft and bearings, which are critical components for a micro gas turbine.
We also collaborated with subject matter experts here at Purdue to validate our component design.
They brought up several opportunities for improvement that we were able to incorporate into our final product.
After the design process was completed, we identified which components could be manufactured ourselves and which ones needed to be outsourced. We tried to keep as many processes in-house as we could so that we could gain more first-hand manufacturing experience. However, some of the parts with more complicated geometries required to be sent to vendors with advanced capabilities.
We used a variety of vendors. Xometry was used for direct metal laser sintering to produce the complex rotors, while lower temperature parts surrounding the compressor were 3D printed out of high temperature resin. Much of the simpler manufacturing was done on campus by Bechtel, and some parts were commercial off-the-shelf parts such as generators and the test balancing kits. Finally, some ancillary systems, such as the containment for testing, were constructed from spare parts and locally available building materials.
This class has full access to Zucro laboratories for the testing portion. Zucro has a variety of integrated testing systems, including standard air supply, heated air supply, propellant systems, and data acquisition and control. Each test cell has a dedicated control room where testing can be done autonomously to ensure safe operation. Our testing plan takes advantage of the majority of these capabilities.
The Bechtel Innovation Design Center here at Purdue was used for their manufacturing facilities. This includes a metal laser cutter for cutting sheet metal, a 5-axis CNC mill for machining the turbomachinery stators, a CNC lathe for fabricating the shaft, as well as a hot workstation for welding several components. External vendors were used for advanced manufacturing processes like direct metal laser sintering for manufacturing the turbomachinery rotors.
We want to thank Professor Qiao for her leadership on this project, and we're looking forward to continuing testing the full gas turbine next semester.